Hello, everybody. My name is Sunil, and we are ThreatMetrix. Today, we'll be presenting how we achieved near real-time ingestion in Hadoop using Apache Apex, Kafka, and Impala by implementing Lambda Architecture. So let's begin with who we are. ThreatMetrix is a digital identity company. It's a market leader in providing a cloud solution for authentication for digital personas and transactions on the internet. It verifies around 20 billion annual transactions by supporting almost 30,000 websites and 4,500 business customers globally. It's used for improving customer experience, reducing friction, and revenue gain. The way it's typically work is when you launch your app or websites, ThreatMetrix receives fingerprints your device, and when customers of ThreatMetrix they do any important event like login or payment processing or registration, they make an API call to ThreatMetrix to receive more insights about the device, about the session, and ThreatMetrix provides risk assessments of that particular session that enables them to do further operations. So it serves a variety of industries: financial services, commerce, payments. It's lending, media, government, and insurance. So what the business problem we are trying to achieve? When customers ask about the device information for a given session, ThreatMetrix responds them with the event they were doing, along with some risk assessments. It calculates around 700 attributes. It's pretty large event. And what the business problem we were trying to achieve is creating an event store of this event, which is an event that our customer created, plus the risk assessment that ThreatMetrix calculated. So the goal was to create an event store I just explained some now what's make an event. It's an API response for ThreatMetrix customers. And these are the three typical events. It's account creation. Login is the most, I think, the high throughput event. And our goal was to create an event store which is always up, it's scalable, it's resilient and extendable. And we are using event store for various purposes. One of the primary purposes is we have a web portal where our customers can interact with data. So it's not a typical big data system where it's only used by analytics. We have actually it's more interactive, where customer not only can query the data in near real time, but they can even respond with attach more details to it. It's also used by reporting and data science for doing keep improving our capabilities, and by accounting for generating billing and getting business insights to it. So that's an event store. Basically, in a technology term, we are creating a data warehouse, and it's in typical way. Data warehouse this is a Wikipedia definition of a data warehouse, which is it's a central repo for all the important events that occurred in the organization. And in our case, our API server is our business system, which generates this data, attaches this event, and our goal was to create an event store data warehouse for this. Again, the difference is that typical data warehouse used by the analytics reporting. In our case, it was meant for more interactive purpose, and that's why there was more emphasis on making the data available as soon as possible, near real time. So this is what we are trying to achieve when we are creating the data warehouse, the event store. It has to be a low latency, so the shortest time between the data generated versus data is available. It has to have faster access, so the query should run faster. When somebody tries to query it, it should be extendable. Our business are growing, so our data volume and it should be extendable by extensible by we should be able to add columns without rewriting the data. So it should be scalable because as our business grows, we should be able to scale by adding more machines without rewriting the entire application. It should be highly available. We don't want single point of failure. We have live applications running which are accessing this data. And it should be resilient. So it should self-heal if there is a network failure or if there is some issue, we would want it to self-heal. And so this is our typical data flow. So our event producers, our API server produces this data. So it produces those events, calculates attaches with risk assessments, different attributes, formats it, and emits a JSON event. And this JSON event is given to a Kafka queue. We are using Kafka for our queuing system. And then we are using Apex to process this Kafka queue. And we are writing to Hadoop. And we have Impala, which is a Cloudera implementation, which gives you a SQL access to data written in Hadoop. So that's our high-level data flow. And let's talk about the data volume a little bit. And so this is the approximate transaction volume that ThreatMetrix gets. So our max volume is around 87 million events per day so far. It changes every year, of course. And our average volume is around 60 million events per day. And our average event size is around 1.7 kilobytes. That makes our daily volume around 144 gigabyte and then it's with 3x replication, it's around 442 gigabyte maximum data. So we at least had to scale our application to achieve this. It can do even more, but yeah. And typical with just daily average volume, it's around we write around 306 gigabyte data per day, with monthly around 9 terabytes to close to 108 terabyte a year. So why Kafka? I think this is a big data conference. I don't have to give much justification to this, but still, it's distributed. It scales. It supports atomic write, so it guarantees that once its data is written, it's available to read. It's highly available. It keeps multiple copy of the data, and it supports really high throughput, and it supports order of one constant time performance, even if if you store terabytes of data. It has explicit support for partitioning messages over Kafka servers and distributing consumption over a cluster of consumer machines while maintaining per partition ordering semantics. So that fits pretty well in our use case. We are using Parquet file format to write data in Hadoop. We're using Parquet because it's a columnar file format. It's also worked very well with Impala, the query engine that we are using. Our typical data access pattern on Hadoop is filtered by some of the important columns. So that's why we we have chosen a columnar file format. It's very it has already high performant libraries to read and write data, so we can use it. We don't always have to rely on an Impala SQL interface to write the data. We are using Impala. It's a query engine on top of HDFS. It's not a MapReduce like Hive, and that's why they are able to achieve a higher performance, because they don't write the intermediate data to the disk like MapReduce. It still has the familiar SQL interface. That all the data scientists and all this already know. It's easy. It has JDBC driver, which you can easily connect to the front-end application and retrieve the data. If you partition your data properly, I think you can achieve a really high performance even on a large data set, because with your partition predicted, it only scans the data that filtered by that matches your partitions predicates that you provided with the query. I can probably skip this, but we are using Apex because it's a Yarn native application. It fits well in our Hadoop ecosystem. It's high performance. I think the biggest feature we all like is it's very fault tolerant. It's very resilient. We had issues where we had a network failure or there is a configuration issue. As soon as we fix maybe a configuration issue, the application didn't need it to redeploy. It retried and it started from where it left. It already had a huge, a big library, Malhar library that comes with a lot of operators that are ready to use. And it already has many connectors with messaging system or databases or files. So that's it. And so our use case is that we wanted to have low latency availability of data, but we are using Hadoop, and we all know that Hadoop doesn't like small files because that overloads the name node. So we had to implement a Lambda architecture, which is by definition it's an architecture where it's where we have a massive quantity of data we're getting streamed, but we combine both streaming processing methods plus batch processing method to make to get best of both worlds. By streaming application, you get the instant data availability. By batch processing, you get the best performant, best data structure that Hadoop likes, and it's best performant. So I'll hand over to my colleague Tim for the next few slides, where he goes through how we implemented this in
I'm on. I'm Tim, engineer from ThreatMetrix. And as Sunil said, we're in fraud detection business. So every transaction we make between customers and our system, it's basically consists of a serious event. And the problem we're trying to solve is how we're going to capture all the event and save them, and at the same time, make it available to our customers and our internal system on a real-time or near real-time basis. So the latency is important to us. And this is the architecture we have. Actually, I need to give credit to another engineers announced he is not with the company anymore, but he initially designed the system. And we need to give credit to him. So we have two passes in the architecture. One is, you can call it a fast pass, which so I believe it's the lower pass on this slide. So it's basically, it's a real-time ingestion of data into Cassandra. So it would immediately available. And then we have a slow pass, which is the upper side. It's a microprocessing. It's a 1-minute batch. So we batch the data in our output operator. Then we purge them on a 1 minute mark. So it would have a latency of 1 minute. And the Cassandra serves the company very well. It's widely used in multiple applications. So we stay with Cassandra on the fast pass. And then the Impala query engine on top, it queries Parquet files, resides on the Hadoop HDFS system. That was new piece. And the Apex real-time streaming really helps us moving the data from our backbone Kafka pipe into our system in almost real-time basis. The latencies on each operator is less than 10 milliseconds. And we took, there is a compaction job. So since Impala doesn't have compaction jobs built in, and we generate a lot of small files because we do a purge on 1 minute basis. And the Hadoop cannot handle small files very well, so we need compact those files. And we run a compact job. Actually, it's helping Impala to deal with the data better. And actually, it's pretty tricky thing to do because when we merge files from small files into bigger files, we are actually touching the active directories that Impala is looking at the same time. So we have to guarantee that we are not interfering with Impala. So we have to do a lot of tricky things to get this to work, which, the Caldera engineer team should take a look at this and have built in some kind of support, and they would relieve a lot of pressures on the communities using the Impala. And we took, this is some our operator organizations, and I think we took a live shot of our production. How do I play this? And it's kind of big, so I'm just go through this instead of.
I couldn't take a screenshot of entire.
So
I took a screenshot video so that to go through the entire physical DAG.
So basically, we have 5 operators. But if we look at that, the first operator was reading from Kafka topics. And then we do the second set operators. Here, in our production, we have 8 instances of every operator. So the second operator is doing some ETL, some formatting. So we call it format operator. So it basically deals with the nominal data and trying to normalize them. And then there is a big switch going on. So we implemented a codec so that we're trying to move the data belongs to the same Impala partitions into a instance of we call the Parquet operator. That generates Parquet files into the same instance. But we can't absolutely do that because we would have another problem. The instance would be unbalanced. So some instance it's overloaded and some instance it's starving. So to solve that problem, actually, we build in the optimization algorithms into the codec so that it only moves, they maximize the opportunity of moving data into a same instance if they belong to the same partitions under the constraint that we have to have a balanced operators, downstream operators. So, and it worked out pretty well. So Apex, apparently, the codec, it does works, and our system running pretty balancedly. And then the set of operators after that is all housekeepings for Impalas, like adding new partitions to Impala tables and refreshing the data, update the compute stats, all that stuff. Our system is, as Sunil mentioned, is handling around 100 million transactions per second. And we are piping through around how much data? Actually, your number is compressed number. So if it's uncompressed, you want it close to 4K. So we're doing 100 million a day. So maybe close to like 300-400 gigs of data into the system. And again, we're using 8 instances for each operators. And we did a stress test on the system. We can easily handle 5,000 TPS per second in this current configuration, and it can run to the upper limit to 8,000. But this is a fully scalable, so we can scale any way we want. We can simply add more operators, then it will handle more transactions. And the system is at least once, so it's pretty nature for Apex. That's a good part of it. We like the at least once guarantees from Apex streaming engine, out of box. And then it has this fault tolerance. It restarts if something outside your app, it's causing it fails. It restarts, and since we are guaranteed at least once, so we're not going to lose any data. And if we could generate duplicates data for the downstream, but our compaction application actually taking care of it. So we just have transitional duplications, which our business can live with. And that's about it.
Yeah, but compaction app is pretty simple. It's
it's another streaming app, but the complexity is not on the Apex side. The complexity is on the Impala side. Which there's a lot of complex things we have to do so that we're not interfering with Impala.